All right, it is 10 and we'll get started. And I do know today's not Friday, March 5th, but Monday, March 8th. We're going to do a little catch up today where we're going to go over the PowerPoint that was for Friday. We should be able to finish that up today and move on to the PowerPoint I had scheduled for today. And we should get caught up by Wednesday, I think. So some announcements. Next week, Wednesday, is your second test. It's going to be like the first test, the way that ProctorU and all that. I have left the ProctorU practice test up, and you have unlimited number of tries to do that. So if you want to check your system again before the real test, that link will always be up for you. I'm not going to do the extra credit for doing it this time, but there will still be extra credit opportunities for visiting with our SI during SI sessions. So do make sure you go to those. Also, going to where we left off on Friday, we were talking about acid and base titrations. And if you go on the lecture problem set from Wednesday that we were covering on Wednesday and Friday, you will see there's question 5 there, which deals with gas evolution reactions. For the sake of time, we are skipping that. So I am not going to ask any questions on exam 2 about gas evolution reactions where you mix an acid and a base and you get gas. So you can just cross that off, write yourself a note. We will not be doing any of that. So with that out of the way, let's actually get to what we are doing today. And that is redox reactions. All right. So a redox reaction or an oxidation reduction reaction is a reaction in chemistry where electrons are being moved from one molecule to another, right? And our terms with this is that if something goes through oxidation, you lose electrons, while if something goes through reduction, you gain electrons. And the phrase that everybody learns in Gen Chem and that I want you to start burning into your memory is oil rig. This is a phrase that will help us remember the oxidation reduction rules, where oxidation is loss of electrons and a reduction is gain of electrons. So oxidation is loss, reduction is gain. And when we say loss, gain, we're talking about electrons. One more thing, remember from our discussion, first couple of weeks of class, electrons are negatively charged. Electrons have a negative charge of 1. So if you're oxidized and you're losing electrons, you become more positive. You become more positively charged because you're losing electrons. Electrons are negatively charged. While if you're reduced, you're gaining electrons, so you become more negative. Again, electrons are a negative charge, so if you gain electrons, you become more negative. So oxidation, positive, reduction, more negative. So what we're going to go over here first, and I'm going to walk you through this, is our rules for determining oxidation states. Okay, first off, what is an oxidation state? So oxidation state is like a system to monitor redox reactions. They're basically a fake number that chemists assign to elements. And the change in oxidation state during a reaction tells us if something was oxidized or if something was reduced, right? So oxidation is lost, reduction is gained. So loss, gain. So if during a chemical reaction, you lose electrons, so you're oxidized, your oxidation state becomes more positive. While if you gain electrons, if you're reduced, your oxidation state becomes more negative. I'm sure this is all very confusing. You're not quite sure what I'm talking about, oxidation states, all this foreign words, all these foreign words. That's okay. We'll go through this in depth. The first thing we need to learn, though, we need to learn how to assign oxidation states. We have to learn how to put these oxidation states to elements. And we have 5 rules. In reality, it's what? 7 rules, because 3 and 4 both have A and B's. For these rules, low numbers trump high numbers. So rule 1 is the most important rule, and that's more important than any other rule. So when assigning oxidation numbers, you start from the top and work your way down. All right, so the oxidation state of an atom in a free element is 0. So what that means is that if an element is just by itself or bonded to itself, we assign that an oxidation number, an oxidation state of 0. So if we go to 1A, we have Ag. Ag is by itself. Therefore, the oxidation number of Ag is 0. It's by itself and doesn't have a charge. So we assign that as 0. Rule 2. Monoatomic ions have an oxidation state equal to their charge. So if we go to B, we see we have Ag now, but now we say there's a +1 charge on this ion, Ag +1. Therefore, to assign the oxidation state, if it's by itself and has a charge symbol, the oxidation state is equal to that charge symbol. So Ag plus has an oxidation state of +1. And if I had a reaction that went from Ag to Ag plus, if I go from 0 to +1, since that became more positive, this is an oxidation event. I went from 0 to +1, that's oxidation. So if there's an element by itself without a charge symbol, it's 0. Yep. If it's by itself and has a charge symbol, the oxidation state is equal to that charge symbol. +1, +2, -2, so on and so forth. So that's rule 1 and 2. That just deals with atoms by themselves. Now, rule 3 deals with molecules. 3a says that in a neutral molecule, so a molecule without charge, all of the oxidation states have to equal 0. So for example here, we have NaCl, and we'll get to these rules. These are rules like 4 and 5, where I'm saying +1 and -1. So we can ignore that for now. But overall, NaCl is 0. All the oxidation states of the individual atoms equal to 0. So if we go to C, CaF2, there's no charge on this molecule. So overall, and I'm going to put it over here because I'm going to fill in more stuff for CaF2. Overall, all of the oxidation states of CaF2 are equal to 0 because it's a neutral molecule. Same thing for D, H2S. Overall, this is a neutral molecule, so all of the oxidation states in that molecule will add up to 0. And you see for E and F, my molecules have charges on them. And so that is rule 3b. If you have a molecule that has a charge, all of the oxidation states taken together must equal that charge. So for CO3 -2, all of the oxidation states in that element have to equal -2. For CrO4 -2, all of the oxidation states in that element have to equal -2. All right, before I go on to rules 4 and 5 now, is there any questions about anything I've done up to this point? All right, so for C, D, E, and F, so far we've told what the total oxidation number is of the molecule. However, for oxidation states, we have to assign oxidation numbers to every atom in that molecule. So we need to have one for Ca, and we need one for F. We need one for H, and we need for S. Carbon and oxygen, chromium and oxygen. And you can notice here, you see it's CaF2, but I only have one F. You could do Ca plus F plus F, H plus H plus S, so on and so forth. The only reason why I wrote 1 is because the oxidation number is the same. So fluorine, you have 2 fluorines, but each fluorine has the same number. That'll make sense in a minute. All right, so rule 4a, group 1 metals are always +1. So in an element, group 1 metals are always +1. If we look at C, D, E, and F, we don't have any group 1 metals. But if we did, it would be +1. Rule 4b, if a group 2 metal is in an element, it has an oxidation number of +2. All right, so in example C, we have a group 2 metal. Calcium, element 20, is in the second column. So it's a group 2 metal. So we know it has an oxidation state of +2. So for this equation, we have +2 plus F equals 0. So all we have to do for C now is to figure out what F is. For the other ones, we have not gotten through their rules yet. So rule 5 is, in compounds, certain nonmetals have oxidation states according to this table. So this table says, and the higher you are in the table, the more important you are. Your rule triumphs. So this table says, if you're fluorine in an element, you have an oxidation state of -1. So -1, -1. So my oxidation states for this, if I was going to write it, it would be like calcium +2, fluorine -1. You can see the math equals to 0. +2 -1 -1 is 0. So all of our oxidation numbers are adding up together to equal 0. So a common mistake I see for something like C. You have 2 fluorines. Each one is -1. You would not say fluorine has an oxidation state of -2. A lot of people will add these together and say, and on the test, like a question could be, I give you the element CaF2, and I ask you, what is the oxidation state or oxidation number of each element in CaF2? And people might put Ca is +2, F is -2, which is incorrect. F is -1. You just have 2 of them. So Ca is +2, F is -1. Right, before I move on to the other elements, anyone have any questions? Anyone like a little lost on what I'm doing here? Let me know. Anyone have questions? Want me back up? Anyone not sure what I got the +2 or -1 from? All right, so we did fluorine, now hydrogen. Anytime you see hydrogen in a molecule, it's going to be +1. So hydrogen +1. Oxygen. Anytime you see oxygen, it's -2. So oxygen -2, oxygen -2. Group 7A, halogens. Always going to be -1. Group 6A, so that's the same column as oxygen, -2. So we do have a sulfur. Sulfur's in group 6A. So that's -2. So D is done. So the oxidation numbers of D is hydrogen is a +1. Sulfur is a -2. Again, if we do our math, we should have 2 hydrogens here. So H plus S equals 0. 1 plus 1 minus 2 equals 0. So we're following our rules there. Group 5A, that's the group with nitrogen, is -3. All right. Now we have to do E and F. So we figured out for E and F, oxygen is -2. But we do not have a rule for carbon, and we do not have a rule for chromium. So we have to figure those out. And all that is algebra. So I'm actually going to let me expand this out. So I'm going to write all the oxygens out. So carbon plus oxygen plus oxygen plus oxygen. Overall, that has to equal to -2 because that is the charge of our element. So carbon, we don't know. However, we do know each oxygen is -2. We know that because of the rule in our table. based on this algebra, carbon -2, -2, -2 equals -2. What must be the oxidation state of carbon? Can anyone tell me for E, what must be the oxidation state for carbon if oxygen is -2? -4, not 4. I meant so this is algebra, right? Let's do our algebra. So the actual algebra equation is x is carbon here. -2, -2, -2 equals -2, right? Yeah. There we go. And so it's x -6 equals -2. Add 6 to each side. The oxidation state of carbon is +4. And that's all. That's E and F are basically as complicated as it will get for oxidation states. So with that, chromium must be, who wants to tell me what chromium is? If oxygen is -2, I have 4 of them, and I add that to chromium and it equals -2, chromium must be +6. Exactly. I'll just do the math again. Chromium plus O plus O plus O plus O equals -2. Chromium -2, -2, -2, -2 equals -2. Running out of space here. Chromium -8 equals -2. Add 8 to each side. Chromium equals +6. All right. Any questions? Now that you saw me work those out, any questions about how to assign oxidation numbers? And a common question I always get is, will we get these rules on the test? No, you will not get these rules on the test, but hopefully I will give you enough examples, and I'll find more examples to put on Blackboard today. I'll give you enough examples that it will kind of like make sense. Like they will start to burn into your brain. And the question you may give, will the total charge be there, and will we have to find the element charges? So if I give you a question, like in E, I have to give you like the overall charge of the molecule. And then I could ask, okay, for like a total legitimate test question would be, what is the oxidation states of carbon and oxygen in this element? And I give you CO3 -2. So I could do that. I would not do like CO3 and keep a -2 hidden and then like penalize you if you didn't realize that CO3 is always -2 charge. Because if I gave you this, the oxidation states say, well, this all has to equal to 0. Oxygen's always -2, then carbon must be +6. Like that would be legitimate. But if I don't give you a charge, that means the charge is 0. All right. So let's do some more practice on this. Oh, I have one more slide talking about oxidation states. All right. So just a few things about oxidation numbers. Oxidation numbers are usually whole numbers. It is possible to get a half a number. We probably will not see any examples in Gen Chem 1 where I give you a problem and expect you to know that like an oxidation will be a half number. Like here for KO2, our rules state that K is always +1. Therefore, for this to be 0, oxygen has to be -1/2. I won't give you examples like that, but be aware that is possible. Oxidation reduction, we already talked about that for oil rig. So when we are losing and gaining electrons, remember electrons are negatively charged. So if you gain electrons, your oxidation state becomes more negative. If you lose electrons, oxidation state becomes more positive. And one more thing to confuse you is the phrase agents. In chemistry, we also talk about oxidizing agents and reducing agents. Basically, in a reaction, if you are oxidized, then you are the reducing agent. You cause something to be reduced if you yourself are oxidized. If you are reduced, then you're the oxidizing agent. You cause something to be oxidized. So again, I'm sure that's a bunch of words that don't quite make sense quite yet. So let's look at some more practice using our oxidation rules. So question 2. I want you to first tell me if we have a redox reaction. So let me define that. A redox reaction only happens if elements change redox numbers. So what that means is if I go from one side of the arrow to another, if my oxidation states or my redox numbers change, then I had a redox reaction. I moved electrons. If the numbers are the same on both sides of the arrow, a redox reaction did not occur. So that's the first part of this problem. Then, if you do have a redox reaction, tell me what the oxidizing agent was and reducing agent. So I'll do A for us. And then I'll let you try and do B. B is actually, so B is easily the most complicated I'll give you. So if it's balanced, there's no redox reaction. It's more like you're comparing, it's not quite balanced. It's you are comparing, for example, let me do A, and maybe that will explain things better. So let me do A and see after doing A if there's still a question like that. All right, so the first thing we want to do is we want to know if a redox reaction happened. So let's assign redox numbers then. Lithium by itself, no charge. Based on our redox rules, that has a redox number or an oxidation state. I'm going to use those two words interchangeably because you can use either one. So if I say redox state, it's the same thing as oxidation number or oxidation state. So lithium by itself is 0. Oxygen by itself, based on our rules, we say if something's by itself and there's no charge, it's 0. Okay, now we have lithium oxide. Overall, there is no charge in this compound, so all the oxidation numbers have to equal to 0. So our rules state, if you are in column 1, your oxidation number is +1. Our rules also state if you're oxygen in a compound, you're going to be -2. We can double check to see if this works out. So we said lithium plus oxygen has to equal to 0. We said lithium is +1. We said oxygen is -2. That is equal to 0. So that is correct. We assigned our numbers correctly. All right, so this is a redox reaction. So that is, yes, it is. Because our numbers, lithium went from 0 to +1, so lithium changed. Oxygen went from 0 to -2. Oxygen changed. That's what I meant by if elements change their redox numbers. from one side of the arrow to the other. If they are different, like the elements themselves, that's a redox reaction. If they are the same, if lithium and oxygen were both 0 on the other side of the arrow, no redox reaction happened. But here they did. All right. Now we need to find the agents. So let's bring up our word of the day again, oil rig. Oxidation is loss, and I'm just going to put of electrons. Reduction is gain of the electrons. So lithium went from 0 to +1. So if I go from 0 to +1, did I gain an electron or did I lose an electron? And remember, electrons have a -1 charge. You lose an electron, yes. So if I lost an electron, that means I was oxidized, which means I am the reducing agent. So remember, once you figure out what something, if you're oxidized or reduced, when it comes to the word agent, it's kind of like the opposite. I know it's confusing, but what this means, if you're the reducing agent, you caused something to be reduced, or you were oxidized. So that's lithium. Now let's do oxygen. Let me get a different color here. Oxygen went from 0 to -2. So I'm going to write my words out here. So if I became more negative, that means I gained electrons because electrons are negatively charged, which means I was reduced, which means I was the oxidizing agent. And notice oxygen, oxidizing, that's where the word comes from, because this oxygen oxidizes everything. When rust forms on a nail, that's a redox reaction. It's oxygen. And oxygen is oxidizing the iron, right? So that's why it's called oxidizing agent. And most of the times, not always, but a lot of the time when you have oxygen going to a compound, that oxygen is usually reduced. It's the oxidizing agent. All right, questions about A? All right, so for B is really complicated. So I'm going to give you a couple minutes for B. Try and put in the oxidation numbers. Then I'll be back in just a couple of minutes to jump right in, because I know B is, there's a tricky thing about B that I haven't talked about yet, because it has to do with polyatomic ions. But I want you to struggle with it a little bit. Then I'll be back to help you out with that. So try assign oxidation numbers to B. All right, I'm sure you're still working, but I want to tell you the trick here. The trick is NO3 and SO4 are polyatomic ions. Remember these, I had that list of, here's a bunch of polyatomic ions that we should know. And the trick is that all of the elements in our polyatomic ions have to equal the charge of our polyatomic ion. So what I mean by that, so let's go for SO4 minus 2. When we do the oxidation numbers for SO4, it's sulfur plus oxygen plus oxygen plus oxygen plus oxygen. They all have to equal -2. And you can see here, it's tricky because there's no -2 here. Because in total, when two sodiums are added to this, and I'm running out of space again, so I'm going to do sodium plus all this. When sodium is added to it in this compound, everything is 0 at that point. Sodium is balancing out the SO4. However, when doing SO4 itself, you have to realize it's -2. So let's go to our rules. Oxygen is always -2 in a compound. I have 4 of those. So overall, like all the oxygens together, all of them together are equal to a -8. And our math was sulfur plus 4 oxygens equal a -2 in SO4. So for that to math to work out, sulfur must be +6. Sodium, group 1 metal, always +1. Same thing as for NO3 minus. Oxygen is always -2. And our math for NO3 minus is nitrogen plus oxygen plus oxygen plus oxygen equals -1. If oxygen is always -2, for this math to work out, nitrogen must be +5. Lead is not a group 1 or group 2 metal. So we can't just look at lead and know what it is. However, lead plus all of these times 2, because I have 2 of these, or I guess lead plus NO3 plus NO3 equals 0. That's what I should do. Overall, NO3 is -1. Each individual atom, nitrogen is 5, oxygen is 2, but overall as a compound is -1. So lead here has to be +2. So let's go back over here. Let's do the other elements. SO4, it's still SO4, so the numbers are the same. Nothing changes there. So oxygen is -2. Sulfur is +6, because SO4, sulfur and oxygen will always be that in SO4. SO4 is overall a -2 charge. So lead plus SO4 has to equal to 0. So that all equals to 0. So lead must be +2. Sodium nitrate. Nitrate again is -1, and it has since NO3 is always going to be the same. Oxygen is always going to be -2. Nitrogen is always going to be +5. Right. Overall, nitrate is equal to a -1. And sodium, overall, sodium is always a +1. And let's check our math. +1 minus 1, that equals 0. It should be this is a neutral compound. And then you look on each side of the arrow and you ask yourself, did any redox numbers change? The answer is no, they didn't. No redox reaction has occurred. This is not a redox reaction because no numbers have changed. So that's what I meant by determine whether each reaction is a redox reaction, only happening if elements change. You're confused. PbSO4, -2 plus 6 minus 2 equals 0. Remember, we have 4 oxygens. So overall, 4 times -2 equals -8. So +2 plus 6 minus 8 equals 0. However, each individual oxygen is -2. Yes, that's what people often get confused on. When writing oxidation numbers, you cannot, like on the test, if I said PbSO4, what is the oxidation numbers? If you put -8 for oxygen, that's wrong. Oxygen is not -8. Oxygen is -2. Then you have to go one step further and realize, okay, if I have 4 of these, in total, all of the oxygens are -8, but each individual one is -2. Yeah, that's the very tricky part. So keep that in mind. All right. Now that you saw me work these out, any questions? Anything that I lost you on or any confusion? And I will find more practice problems for redox reactions so you can get more practice on these. All right. So combustion, I think for the sake of time, we're going to skip combustion reactions. So combustion reaction, I'll just briefly say it, but I'm not going to test you on it. A combustion reaction is a redox reaction where you have oxygen and you are combusting something with oxygen. And usually, every time you do a combustion reaction, you always make carbon dioxide into water. And also, to have any type of combustion reaction, you need oxygen. So that's why if you want a candle to go out, if you just cover the candle will go out because it doesn't have oxygen anymore. Oxygen only works, or sorry, fire only works in the presence of oxygen. That's also why you see an oxygen tank has a big old flammable sticker on it, because that thing will explode pretty good. But we're not going to do problems on that since we need to do a little catch up with the winter storm and all. So that is the end of the PowerPoint from Friday. We're going to skip question 3. And I'm going to hop to the PowerPoint I had scheduled for today. Again, obviously we won't finish it today. But the idea is we will plug away at it and be caught up by Wednesday, hopefully. So let me get this up. Problem set 16. Let me share my screen. All right. So we're going to just probably go over 1 or 2 slides here. And what we're going to be talking about is pressure. We're going to be talking about gases. And so what a pressure is any pressure is due to atoms hitting you or hitting a surface. So pressure equals force divided by area. And so the bigger pressure you are feeling, that's due to a stronger force hitting you. So on the top right of our image here, we have an example of gas hitting a wall, right? When you hit that wall, you get a force, and that is causing pressure. The way we hear, the way you're hearing me right now, is that out of your computer or your phone, you have sound waves coming out. These sound waves are hitting your eardrum as a pressure. Your brain is taking the pressure felt by your eardrums, making that an electrical signal to send to your brain. Your brain interprets that electrical signal as language. And that's all due to pressure hitting your eardrum. Under areas of high and low pressure, your body, when talking about your eardrum, you have pressure going each way, external pressure from the environment and internal pressure from your body. So when you go up on the airplane, the pressure changes and you feel your eardrums pop, because under normal conditions on sea level, these are in equilibrium. But if you're in areas of low pressure, your eardrums can pop outward because your body's pressing against it. And if you get in low pressure enough, your eardrums will actually rupture because your outside force is too much. There's nothing pushing against it. Same thing can happen in the opposite. If you go to too high of a pressure, then your eardrums will push inwards and then they'll eventually pop because it's too high of a pressure. Low pressure systems, high and low, that just says, again, what is the force of the gas that is being felt in the environment? And for density, I know the words are cut off here, so let me rewrite them. This says low pressure. And this is higher pressure. So the density of a gas directly relates to its pressure. The higher the density, the higher the pressure. And this happens when you go to fill up your tires in your car with air, right? When your tires are low pressure, what do? You go to some gas station or some store. They'll put air inside your tires, increasing the pressure. What is this doing on a molecular level? You're increasing the density of gas in your tires. You're causing more gas to hit the outside of your tires more often, creating that pressure. Because remember, pressure is force divided by area. And on Wednesday, we will continue this discussion where we talk about gases in terms of chemistry. So we have different laws we're going to be talking about. This should take us about 25 minutes to a half an hour to cover, and then we'll get into the lecture I have prepared for Wednesday. But are there any questions about anything that we have covered today up to this point? If not, remember our test next week, Wednesday. I will tell you what materials cut off. Again, it's always in the test 2 folder. I will find more example problems for redox reactions and put those online for Blackboard for you to practice. I will put a homework as always. If you have questions, always feel free to email me. Otherwise, I hope you have a good week this week, and hopefully I will see you on Wednesday. Take care, everybody. Have a good one.